my YouTube channel. I'll give it the old college try anyway. Okey-doke, here we go. Organic Chemistry 1, Chemistry 3101. This is Chapter 9, which is the Alkynes chapter. Way back at the beginning of this class, we went over all of the functional groups that you need to know in Chemistry 3101, and one of them was the alkyne. And an alkyne is when we have a triple bond between two carbons. So two carbons with a triple bond in between them like that. Not to be confused with alkenes. An alkene, I'll just scribble it up here in blue. An alkene, which was with the focus of Chapter 8, is when we have a carbon-carbon double bond. And then we have our groups or hydrogens around that. So alkynes, carbon-carbon triple bond. And we're going to study all the chemistry of alkynes and the nomenclature of alkynes and some cool reactions and even how to make an alkyne. So let's get to it. All right, alkynes are molecules that possess a carbon-carbon triple bond. What you see here is an orbital overlap diagram of acetylene. And if you've ever done any welding, you've probably heard the word acetylene. So what's drawn here is this, okay? They're just kind of tilting it on an angle, but this is the simplest possible alkyne that we can have. It's C2H2. Can't get much simpler than that for an alkyne. And what they're showing here, the gray orbitals attached to the carbons, these are the sp hybrid orbitals, so sp, sp, sp. And we know that the sp orbitals overlap to form a sigma bond, whether it's between the two carbons or between the carbons and the hydrogen. So again, this would be a sigma bond. The first bond is a sigma bond, and then we have another sigma bond. But we know that the two other bonds, and I'll just use the green highlighter for these, that both of these bonds are pi bonds. And how do we make a pi bond? Well, a sigma bond is made by the head-to-head overlap of two orbitals, whereas a pi bond is made from the side-to-side overlap of two orbitals. So if we just highlight one of the pi bonds, I'll just kind of trace the p orbital or one of the p orbitals on this carbon in green like this. So there's one p orbital, there's the other p orbital. They're in the same plane and they overlap. Now they're not shown as touching here because it just kind of makes the orbital overlap diagram a little difficult to read, but these dashed lines mean that they are touching. So that's one of the p orbitals, that's one sigma bond. And then the other one, you can see we have one that's perpendicular to it on each of the carbon atoms, and there's orbital overlap between the two. You can see the little dashed line back here. Anyhow, so the idea is that we have side-to-side overlap of p orbitals, right? Again, here they're not shown as overlapping, so we draw a dashed line in between the two like that to say they're touching, and that is what makes the pi bond. Who could answer this question for me? What would be weaker, a sigma bond or a pi bond? And this is not intended to fool you. I'm just seeing if you remember which one would be a weaker bond, a sigma bond or a pi bond. Absolutely, yes. My students are answering the pi bond. So a pi bond is weaker than a sigma bond. All of my students are 100% correct. That's a good thing. So let's move forward. And if you look at the electrostatic potential map of an alkyne, it's shown here. And again, this is just acetylene. So what we have here is the electrostatic potential map of this molecule, the simplest possible alkyne. And we know from previous electrostatic potential maps that when we have a region that's shaded in orangey red here, that represents an area of high electron density, whereas the blue regions represent areas of low electron density. Therefore, we can see that most of the electron density resides between the two carbon atoms, and that makes sense. We have a triple bond in there. We have a total of 6 electrons being shared between the two carbon atoms. And so since we have those 2 pi bonds between the two carbon atoms, that gives alkynes the ability to behave as nucleophiles. So it says a pi bond here, the pi bond of an alkyne, can act as a nucleophile. Many of the addition reactions that we saw with alkenes are going to work on alkynes, things like halogenation, hydrogenation, hydration, and we'll look at some others as well. Well, if you're wondering, I understand acetylene, Mr. Dion, and I've heard of that because acetylene, again, which is the simplest possible alkene. It's just this, and it's going to come up a lot today. We're going to use it in synthesis as well. Acetylene is used in welding. So if you've ever done gas welding, well, the gas that we use in gas welding most of the time would be acetylene. And the reason why welders use acetylene as a gas in blowtorches is because it causes or produces such a hot flame. I think the flame burns around almost 3,000 degrees Celsius or something like that. And there's also been many alkyne groups found in natural products. This is an interesting one here. This is called histrionicotoxin. And this compound is isolated from Dendrobates histrionicus, which is also known as the poison dart frog. And you can see there's actually two alkynes in here highlighted in green. And what the ancients would do is they would take, the frog and they would extract, or I won't go into the details of how they would get the frog to sweat, and then they would dip the tip of the arrow in the frog's sweat, and this is a poison, a potent poison. So they would shoot their prey with the arrows that had this poison on it. So something kind of interesting there. I'll just put this out there as an FYI if you've read the textbook, and I encourage you to do that. There's an interesting example of a contraceptive that is used that also has an alkyne in it. I won't be quizzing you on that, but that might be something you would like to take a look at. Well, let's move on and talk about how we would name an alkyne. If we're going to be working with alkynes, I have to be able to communicate with you. You've got to be able to communicate with me. And scientists all around the world have to be able to communicate with each other and give each alkyne an unique, unequivocal name that they can use to communicate. So let's see here. Alkynes, good news, are named using the exact same procedure that we used in chapter 4 to name alkanes, just a few modifications. In fact, I would even add to this and say that if you understood the nomenclature of alkenes, alkynes won't be much of a stretch, because much like alkenes, when we're naming an alkyne, we have to find the longest carbon chain that possesses the carbon-carbon triple bond. We can't just go with any long chain. It's got to have that triple bond in it. Then we identify and name the substituents. We're getting into the, last couple weeks of the course. I'm sure that by now you've really polished your ability to name and recognize isopropyl, isobutyl, sec-butyl, tert-butyl, ethyl, methyl, all those different groups, chloro, bromo, etc. So make sure you can identify and name those. Then we provide a locant, which is nothing more than a Tsatsi name for a number. For each substituent, we give the carbon-carbon triple bond the lowest possible number, the same way we did it with alkenes. We put all the substituents before the parent name. We ignore prefixes except iso, cyclo, and neo when ordering alphabetically. And you got a couple of options for the triple bond locant. You can put it either just before the parent name, or you can put it just before the -ine suffix, and I'll try to remember to show you an example of both of those. So there you go. Again, if you spent a lot of time on alkene nomenclature and alkane nomenclature, well, here's a payoff, okay? You're going to really be able to use all those skills to help you name alkynes. Let's take a look at some examples. We'll start out with an alkane, 5 carbons. We would call that pentane. And then we said, okay, well, if you have a double bond, you would call that pentene. Now, of course, you would call this 1-pentene because you want to give the first carbon of that double bond the lowest possible number. And then if we have a triple bond, we call it pentyne. And again, we want to give that first carbon of the triple bond the lowest possible number. So we would call this 1-pentyne, 1-pentyne. Now, you remember the last rule says that you could place the locant, this number, before the parent name or just before the -ine suffix. So the way you would do that is just to put pent, 1-ine. Again, both are perfectly acceptable. Nothing wrong with either of them. The next one, number 2, might look familiar to you. I think we basically used the same example or something very close to it for the alkenes. If we have this alkane here, what do we look for? We just find the longest carbon chain, no questions asked. However, if you look at the compound on the right here, the longest carbon chain does possess 8 carbons, but it does not possess the triple bond. The one that's highlighted in red would be the correct parent chain. because it does possess the triple bond. So you'd start numbering 1, 2, 3, 4, 5, 6, 7. So this would be a 3-propyl because we have a propyl group. 3-propyl, 1 heptyne, or you could call it 3-propyl heptmonine. Either one is perfectly reasonable. Let's take a look at our substituents. Remember that we want to give that carbon-carbon double bond the lowest possible number. It's got nothing to do with looking at all the substituents, finding out what their locants are, tallying up numbers. It's got nothing to do with that whatsoever. We just want to give that carbon-carbon double bond the first carbon, the lowest possible number, and then we just number all the other substituents as is. So if we take a look at the example here that says correct by it, we have some kind of 2-heptyne, and then we have methyl groups at carbon, 2 methyl groups at carbon 5, 1 at carbon 6. So we would call this, let me see if I can scribble this in here, 5, 5, 6 trimethyl 2-heptyne. There you go. Give me a thumbs up if you're with me on that. Just if that name makes sense. And if you're not, don't hesitate to put a thumbs down and just say, hey, Mr. Dion, could you re-explain that or cover that again? Okay, good. Let's see here. Oh, there's a little kind of addendum here at the bottom. This is a trap that students will fall into sometimes. So let's go over it carefully. It says the locant is 1 number, not 2. So you don't call this, 2,3 heptyne. No, you just go with the first number, the lowest number. So if the triple bond passes through carbons 2 and 3, it's a 2-heptyne. If let's say it passed through carbons 3 and 4 of a nonine, it would be 3,9,9. That's the kind of rationale we want to take there. What else? List and number the substituents. Students usually don't struggle with that. By now, students are pretty rock solid on the alphabet. So cyclo and neo, we don't want to forget those. And then I showed you how to apply this rule here to put the triple bond locant either before the parent or before the suffix. Either one is totally fine. There's nothing wrong with either of those. You remember we talked about common nomenclature of alkyl halides, and we even talked about nomenclature or common nomenclature in alkenes a little bit when we looked at ethylene and styrene, things like that. Well, there are some common names that are useful for alkynes, and that's when you have a derivative of acetylene. Now remember that acetylene is just a carbon-carbon triple bond with a hydrogen on each side. So if you put something at this side that you can name and something on this side that you can name, like a methyl or an ethyl or a propyl or an isopropyl, then you can use a common nomenclature system. So it says you look at the R groups. So there's only one here, so you'd call that methylacetylene. Here you've got 2 isopropyls. It would be diisopropyl acetylene. Here you've got 2 different ones. You've got a phenyl and a propyl. In that case, we go by alphabetical order, so A to Z, and pH comes before PR, so phenyl, propyl, acetylene. Another thing that you're going to hear me say is a terminal versus an internal alkyne. In fact, we're going to talk about terminal alkynes a heck of a lot, okay? Even more than internal alkynes.